pedestal supports a load P at its center as shown. If the material has a mass density rho, or in other words rho g is its weight density, determine the lateral dimension. It should be W as a function of Z, so that the average normal stress in the pedestal remains a constant. The cross section is square. It's a mistake. Let's correct it. Okay, how do we go about? The first thing that we do is, let's see what is the stress just below this top head. It is nothing but sigma normal average is equal to P divided by W1 square. Let's call this as P by A naught, where A naught is the area. Okay. We seek to have the same value throughout this particular pedestal. So let's now cut along an area which is about Z from the top. From the free body, we can find that the total load, normal force acting on that area, is equal to P plus the weight above it. So let's write it down. P plus the weight above it, let me call it as W, divided by the area at Z should be equal to this. Let's now call this as some C. Okay, we'll change this later. Let's expand W now. What do we get? We have P plus integral rho G times area, which is A of Z, times dZ, going from 0 to Z. Let's take A to the side. We'll get C times A of Z. In order to get an equation that can be easily solved, let's differentiate both sides. If we differentiate both sides, we get rho G A of Z is equal to C dA Z by dZ. Right? This now I can write as dA Z by A of Z is equal to rho G by C times dZ. Right? Now if I integrate both sides, I get logarithm of A of Z is equal to rho G by C times Z. Boundary condition is at Z equal to 0, we have A is equal to A naught. So we substitute now and find out what would be A of Z. Once we find out A of Z, it is square root of A of Z, which is equal to W of Z.